Okay, so we will start this second session. Welcome back. We will only have one talk in this session, and then the lightning rounds for the posters. Christian is going to present this talk, and the topic is typical thermalization of low entanglement in the States. So, yeah, thank you very much and enjoy.
Thank you. So, first I would like to thank the organizers for inviting me to present this preprint of this title, which was a collaboration at Berlin between me, Clara, Wassner, Giacomo, Guarnieri, and Jens. I think topic-wise, this talk is different from the others that we've seen, but I hope you find it interesting anyway. So the talk is about thermalization and in isolated quantum systems. And so I will start talking a little bit about thermalization in general. And as a general principle, thermalization can be seen as a sort of loss of information. And so as an example, if I have like a box, an isolated box divided into two chambers, and I have a gas in each chamber, and the gas in one of the chambers is hotter than the gas in the other chamber, and then I remove the one in the middle, the gases mix, and I get something that's somewhere in the middle, some equilibrium state where the gas is lukewarm. But the issue is that if the situation were reversed, and if the hot and cold chambers were switched, and I do the same experiment, at the end I get the same exact final state with the gas at the intermediate temperature. So somehow the information of which side was hot and which side was cold was lost. But of course, isolated systems cannot lose information. That's kind of by definition. And in particular, the question is how can an isolated quantum system ever thermalize, since here we have two different distinct initial states, and they both somehow flow to the same final state. And so this is a simple thought experiment, but people have done this actual experiment in a quantum version of it. This is from a paper from 2012 of Trotsky and co-authors, where they prepared a chain of bosons such that only the even sides contain particles in the initial state, and then they turned on some local interaction and let it evolve in time. And you can see that the number of bosons on all sides starts from 0, but as time goes on, it equilibrates to something near 1/2. So somehow we lost the information of whether the particles were on the even or the odd sides in the initial condition. And it's not great mystery where this information went. Of course, we're only keeping track of a single observable, and there are plenty of other observables that could betray what the initial state was. But sort of the effort of trying to show thermalization in isolated quantum system is the effort to formalize what is happening here, and how come the information can never get lost, but somehow it gets hidden, and it's not observable anymore. So I've been blathering a little bit about thermality and thermalization. I still haven't said what a thermal state is, and you probably all know from like statistical mechanics. But let me give some intuition. So first of all, a thermal state is a state which is it must be in equilibrium. So if we have some Hamiltonian, it must commute with the Hamiltonian. And I will assume that the Hamiltonian has no degenerate eigenvalues, just for simplicity, such that in this case, the thermal state will be just diagonal in the eigenbasis of the Hamiltonian. I denote the eigenstates by this mu. And so we can just stop thinking about quantum states. We can just think about probability distributions or the eigenstates. And the second point, which is much more vague, is that a thermal state should contain no information, whatever that means, about the initial condition, except naturally for conserved quantities. So namely, if the initial state had some expectation value for the energy, E, then the equilibrium thermal state should also have the same expectation value for the energy, because energy is conserved. So one way in which this is modeled historically is the microcanonical state. So we have that our state, we know that the state has some average energy E, and so we suppose that the actual state is contained in some tight window around this energy, but we don't know which state in this window, and we don't know anything except for the fact that it's contained in this window, So inside the window, we pick just a uniform distribution. And another possibility, which is a bit more information theoretic friendly, let's say, is that we just fix the energy as a constraint and we maximize the entropy. And this yields the canonical state or the deep state that everybody's familiar with. And here the inverse temperature beta is just determined by the energy constraint. Right, and so thermalization would be the property of a system equilibrating to a thermal state, right? But the problem is that all of these states that I have mentioned are mixed. So the question is, how can we ever obtain them from unitary evolution? And this gives me an excuse to talk about what is happening in equilibration. So I said thermalization is the system equilibrating to some thermal state. But equilibration means that if we have some observable O and we track its expectation value as a function of time, it will start by oscillating and doing some weird stuff. But then after a while, it will just settle down around some equilibrium value. And let's just assume that this happens. You can prove that this happens with relatively, with generality, with some generality, but let's just assume it happens. And if it does happen, then the time that the system spends in this equilibration regime is much, much shorter than the time that it spent in this equilibrium regime, which means that if we want to extract this equilibrium value, we can just take the time average over the whole history of the observable, and this O average will emerge because it dominates only in the average. And like this, we can define this equilibrium state that just extracts this time average. As you can see, the equilibrium state that we get out of this definition, as expected, is also diagonal, a mixed state which is diagonal in the eigenvalues of the Hamiltonian. And I want to stress that this is never the actual state of the system, because if I start from a pure state, the system will always be in a pure state under unitary time evolution. But this state well describes the dynamics of the system for most times. And so we define this as the equilibrium state of the system. And so we get a state that somewhat resembles the thermal states that we get before, which is just a probability distribution over the eigenstates. So the setting in which we work is that we have a local Hamiltonian of some lattice of n sites and some initial state which is a product state. And all the results can be generalized to states with low entanglement, but I will restrict the talk to product states for simplicity. And so this state, if we evolve it for a long time, it will have this equilibrium state, as discussed in the previous slide, which is some probability distribution. And since the state is a product state, it was proven by Amar Anshu that actually the state is kind of restricted in a window, kind of like a macrocanonical state with some very fast decaying tails outside of the window, and the window is more or less outside root n. But the problem is that whatever is inside this window looks nothing like a macrocanonical state. And of course, this is a very naive way of putting it. Nobody thinks it should. But this is just to illustrate the fact that since we are sort of pretending that many different initial states give rise to the same final state, which would be this flat macrocanonical distribution, which is just not possible under unitary evolution. So to kind of solve this problem, we want to define some state which is more similar to what we would expect the equilibrium state of a many-body system to look like, but that still we can call a thermal state. So first of all, I have defined two different notions of thermality, this microcanonical and this Gibbs state. But actually one can show that they are equivalent, and there are many such results, but the one we want to focus about is this one by Brenda and Clara in 2015, where you can define a local state distinguishability measure, which I will not write down in full, but just know that if this DL of two states from sigma is small, it means that rho and sigma can never be distinguished if you're only allowed to do local measurements on the lattice. And what Brenda and Clara proved is that under the right conditions on delta, on beta, etc., the microcanonical and the canonical state can never be distinguished if you're only allowed to make local measurements. So these two notions of thermality are the same as long as you only have access to the system locally. And so we want to do something similar, But instead of considering the microcanonical ensemble here, we want to consider some state which we think could be closer to what the equilibrium state of a many-body system looks like. And so we define a sort of generalized microcanonical state, which is, we take the state restricted in some window of size big delta, and inside this window, we divide this window into many smaller windows, small delta, and inside each of them, we define a small microcanonical state, and we just take the mixture of these many microcanonical states. And we show that under the right condition of big delta and small delta, this state is still equivalent to a thermal state. And this is just by adapting the proof of Clara. And similarly, by adapting this proof, we show that, well, since these steps are still kind of unphysical to pretend that the equilibrium state would have this kind of discrete steps. And so we show that if you have a state that doesn't have these steps, instead it's kind of wiggly, but still it has an entropy which is close enough to the entropy of this stepwise uniform distribution, then this is good enough. This is also a thermal state. So now we have ourselves a kind of state that is thermal. We can show that it can never be distinguished from a deep state if we only have access to local observables. But also it sort of looks more like a reasonable state than just a simple microcanonical state. So all that's left to do is to take local Hamiltonian and an initial state and show that the equilibrium state has a large enough entropy. The problem is that we don't know how to do this. And so what we do is that we force it to have a high entropy by modifying the Hamiltonian accordingly, and then we check what the damage is, essentially. So what we do is that we generate, how can we generate these sort of thermal states from time evolution? We take the Hamiltonian, and it has this decomposition into eigenvalue and eigenstates, and let's say that this line is the spectrum of the Hamiltonian, and we divide the whole spectrum into small windows of size delta. And inside each of these windows, we define we draw a unitary from the uniform measure, from the Haar measure. So we draw a random unitary that only mixes the eigenstates that lie inside this window. And by taking just the direct sum of these unitaries, we basically get a big random unitary that only mixes eigenstates with eigenvalues that are at most of the distance delta with each other. And then we just define our H prime, a new Hamiltonian, which is UHU dagger, and we use this to evolve the system. And from this, we get some equilibrium state. So what do we get from this? From this, we get if we choose delta appropriately, with high probability over this randomness of picking the unitary at random, and assuming the initial state is a product state, we get that the equilibrium state is locally thermal, meaning that at equilibrium, doing local measurements will never allow us to guess the initial state and will never allow us to distinguish the equilibrium state from a simple Gibbs state at the right temperature. And this distance is just some decaying polynomial in the system size. But then it's very legitimate to ask, okay, but what is H prime? I wanted H. I don't care about H prime. So what is the relation between H and H prime? What does this unitary do to the Hamiltonian? So the first thing that we can say is that H and H prime are not completely unrelated, and namely the Gibbs state of H prime and the Gibbs state of H are indistinguishable when one only looks at local observables. So in a sense, the thermal properties of the Hamiltonian are not affected by this local rotation. And we can say a bit more. That is that, well, since we are only mixing eigenvalues separated by an energy difference delta, of course, the smaller delta is, the less disruptive this random unitary will be. And we can show that the time if we evolve a state using H, or if we evolve a state using H prime, these two states are indistinguishable up until a time that scales like 1 over delta. So the kind of situation that we have is that if we evolve a state if you follow the expectation value of an observable using H or H prime, So if in black we have the time evolution of H might not thermalize for what we know. We cannot say whether H thermalizes or not, but we know that there are all of these Hamiltonians surrounding H within a distance delta, which if you actually implemented H prime instead of H in your experiment, you will never know unless you do a simulation that goes longer than a time 1 over delta. So up until a time more or less 1 over delta, the two Hamiltonian dynamics are indistinguishable. And H prime is guaranteed to thermalize. So in a sense, if it's unreasonable to implement the Hamiltonian to within a precision that is smaller than 1 over delta, you will not observe. It's impossible to, well, it's not impossible, but it's unlikely that the Hamiltonian will be observed not to thermalize in a sense. So the legitimate question now is, well, how large can this 1 over delta be? Because if delta is super large, then this 1 over delta is super small, and this is not very interesting. Well, we show that 1 over delta must be taken to be smaller than n to the kappa minus gamma, where gamma is some constant, which we don't care about. It can be chosen to be arbitrarily small. And kappa is another constant that then depends on the Hamiltonian. And this is something related to something called the Darby-Assine error, and I can explain what it is later if you're interested. And importantly, this can be 0. In the worst case, you can construct pathological cases in which the Darby-Assine error is, or in which this kappa parameter is 0, which means that whatever you do, 1 over delta will decay in the system size, which means that this distinguishability time, the time after which H prime can fool you into thinking it's actually H, is extremely small and goes to 0 as you increase the system size. But if kappa is larger than 0, which we believe to be true for generic systems, then this delta, 1 over delta, can be chosen to increase polynomially in the system size, which means that as you go towards the thermodynamic limit, this time at which H and H prime sort of diverge, so at which you can actually distinguish H and H prime by doing some experiment, it becomes larger and larger in the system size. To conclude, we show that any Hamiltonian is sort of surrounded by Hamiltonians, H prime, such that the Hamiltonian H and like the whole circle of Hamiltonians surrounding them, they have indistinguishable Gibbs states. All of these Hamiltonians surrounding it thermalize, and all of these Hamiltonians surrounding it under some assumption on the spectrum of the Hamiltonian, which is this kappa, are indistinguishable from the original line in a short time. So in a sense, up to some finite precision error, these Hamiltonians are sort of guaranteed to not guaranteed to thermalize, but they are very, very close to Hamiltonians that thermalize. And we have, of course, many open questions. So we believe this property of kappa being larger than 0, so of this distinguishability time increasing with the system size to be sort of generic, but we cannot yet construct explicit examples in which we can prove that this kappa is larger than 0. We have some numerical evidence, but an obvious open question is to find a more physical condition. Then, of course, there's this fact that, okay, I said that all of these Hamiltonians are surrounded by Hamiltonians, which are obtained by this weird block diagonal rotation. But if we're talking about like finite accuracy in some thermalization experiment, like the one I showed in the second slide, we have no idea what this block diagonal rotation is. And it would be really nice if we could somehow relate this to some more physical uncertainty. For example, I try to implement some Hamiltonian, but I have some fundamental uncertainty about the parameters or some uncertainty about my implementation, such that even if I try to somehow fine-tune the Hamiltonian not to thermalize, this uncertainty will make it so that actually with high probability I land onto one of these surrounding thermalizing Hamiltonians. And finally, I didn't mention it explicitly, but of course, let me just go back one slide. It might be that this equilibration time, so there's a time after which the system appears equilibrated, it might be that this comes after this divergence time, which means at this point that the two Hamiltonians will never actually diverge, because by the time they are supposed to diverge, because the 1 over delta time has elapsed, they are already at equilibrium, so there is no dynamics going on anymore. And so if we could find Hamiltonians where this equilibration time is smaller than this 1 over delta, then we could actually claim that these Hamiltonians probably locally thermalize. Because you will actually never know if you implemented H prime instead of H. And yeah, with this, I thank you for your attention, and if there are any questions.
Thank you very much. Are there questions?
Yes.
Yes. Did you try other notions of randomness in this unitary? It doesn't have to be drawn from hard random.
Right. For most of our results, A2 design is sufficient. So you need much less randomness than hard random. Actually, we got some complaints that hard random is way too random because you can make some unphysical conclusion from high randomness. But actually, I think the same unphysical conclusions cannot be made by A2 design. But maybe you were looking for some more physical kind of randomness, or I don't know.
I mean, you could consider more physical randomness. That would be one way to address it. Maybe some of these properties change if you change the randomness, right? So
right, yeah. The ideal thing would be instead to have like some explicit like eigenvector mixing randomness, to have some randomness at the level of the parameters that define the Hamiltonian, and somehow show that this implemented to design locally in energy. But this seems very difficult. We are trying to do things in this direction, and it's very interesting, but we don't know yet.
Anyone else or Zoom or something? I think we still have some time. I'm a bit puzzled about, or you're talking about this indistinguishability on this local sense of your lattice, and I wanted to ask if that locality is something imposed by, like technically imposed, or is some regime that you want to look at for some particular reason, or just because it has these nice properties?
So a bit of both, of course. So the one answer is that you have to restrict the set of observables you're looking at, because since the system is isolated, there will always be some observables that do not thermalize. Like if you just take as an observable the fidelity with some states, and you pick the target state to just be, okay, and now I time reverse the evolution that I've done, and I compare with the initial state, this observable will always tell you what the initial state is. So like the idea of thermalization in isolated systems is that you restrict to a set of observables that you think are somehow physical, and you show that if you only have access to these physical observables, you will observe thermalization. And why local observables? Well, on the one hand, they are nice, and it's nice to prove things with them. On the other hand, it's sort of sensible that you would have access to local properties and not global ones. This is not always true, of course. And I suppose there will be other classes of observables for which this works. Yeah.
Yeah, well, thanks for the nice talk, and congratulations on the very nice results. I was wondering, maybe for the conclusion, maybe you would rather want to turn this story on its head, no? And because, for example, we know Hamiltonians that definitely will not thermalize the Gibbs state. When you have additional symmetry, you conserve quantity. If it even converges, it must be another state. So you could conclude from that the thermalization takes longer than this divergence time for that particular one. Right? So it's a lower bound. It says, oh, it's kind of slow. Because if the divergence time was smaller, sorry, if the equilibration time was smaller, well, it would be distinct from the one with the Gibbs state, and which doesn't have the conserved quantities.
It might be, I haven't thought about this in this way, and other conserved quantities are sort of erased by this plot diagonal thing.
Only the energy survives.
Right, only the energy survives. I suppose you're right, but I also think you could adapt this thing to include other conserved quantities, and then you work in the shared diagonal basis of all the conserved quantities.
Yeah, but that's what I'm trying to say. I'm saying that this is maybe also an interesting conclusion.
Yeah.
If you have a Hamiltonian that you know has a symmetry, this argument gives a lower bound on the time it will need to equilibrate.
Oh,
Just
I see what
because
you
of the
mean.
basis of the symmetry.
Oh, assuming you have a nice lower bound on delta. Oh, upper bound on
sure.
delta.
Okay.
Yeah. Oh, yeah. No, thanks. Yeah, I hadn't thought about this.
Anyone else? Any? No? So let's thank the speaker again.
Thank you.